Hey there, focus learners, and welcome back to the Explainer. Today, we've got a seriously fascinating journey ahead of us. We're going to completely demystify the anatomy of a computer. We'll be breaking down the exact physical components that process, store, and communicate the endless streams of data that, let's face it, we all rely on every single day. Okay, let's dive into this.
Here's the blueprint for our anatomical journey today. First, the system ecosystem. Second, inside the CPU brain. Third, RAM and ROM workspaces. Fourth, the backing storage vault. Fifth, input and output bridges. And finally, number 6, the system in motion.
Section 1. The system ecosystem. Hardware and software.
So when you look at a computer, what you're really seeing is this incredibly beautiful partnership. On the outside, you've got the hardware, right? The physical components you can actually touch that execute the instructions. But wrapping around the core of this entire ecosystem is the software. These are the invisible instructions that direct the whole system. Because without software, the hardware is just a heavy box of inert metal and plastic. It's those invisible commands that actually bring the physical machine to life, telling the processing and storage centers exactly what to do.
Now let's see how this all builds if we literally peel back the computer case. When we strip away that exterior, we reveal the motherboard and the 4 core internal components that do the absolute heavy lifting for literally everything you do on a device.
To give you a strong mental anchor for the rest of our anatomical breakdown, we're going to define these 4 pillars right up front. First, we have the Central Processing Unit, or CPU, which acts as the brain of the whole operation. Second is the Random Access Memory, or RAM, serving as your highly active temporary workspace. Third is the Read-Only Memory, ROM, functioning as a permanent instruction manual. And finally, the Backing Storage, which acts as your massive permanent vault.
Section 2. Inside the CPU brain, the Central Processing Unit.
In modern systems, this brain takes the form of a microprocessor. It's just a single, tiny, integrated circuit board, safely housed right there on the motherboard. But the core function of this little square is absolutely monumental. It interprets and executes every single command flowing from the hardware and software. I really want to emphasize this. Absolutely nothing happens in your computer without the CPU's direction. It is the ultimate master control.
Now, what's really interesting about this slide is how the internal structure reveals almost a split personality inside that chip. The CPU is essentially divided into 2 highly specialized engines. On one side, you have the control unit, or CU. Think of this as the ultimate traffic director. On the other side, you have the arithmetic and logic unit, the ALU, which is your calculation engine carrying out all the actual mathematical and logical heavy lifting.
And that traffic director, the control unit, is constantly running a lightning-fast 3-step engine loop just to keep the entire system alive. Step 1, it fetches instructions from the computer's memory. Step 2, it decodes those instructions so the machine actually understands them. And step 3, it executes the sequence, directing the other components on exactly what to do. Fetch, decode, execute. Boom, boom, boom. This loop literally happens billions of times a second.
Section 3. RAM and ROM workspaces, internal memory.
Let's take a breath and step away from that high-speed processor for a second. Computer systems rely on 2 very distinct types of internal memory chips to manage data efficiently. The first is RAM. You can think of RAM as your active drafting table. It's where the computer places data, files, and parts of the operating system that it's actively using right this exact second. The second is ROM. Imagine ROM not as a table, but as a locked permanent safe. Inside this safe sits the totally crucial boot file, also known as the BIOS. This is the basic input/output system manual that tells the computer exactly how to wake up when you first power it on.
But here's where we find a built-in tension in the system's architecture. It's a concept called volatility. Because RAM is designed for pure speed and temporary work, it's highly volatile. The very second the power switch flips off, everything on that active drafting table just vanishes into thin air. ROM, on the other hand, is non-volatile. Even when the power is completely cut, that locked safe permanently retains all of its data.
Let's put these 2 side by side so we can really see why your computer needs both. RAM is temporary, it's volatile, and it's heavily reliant on a continuous read and write status so it can function as a dynamic workspace for your active programs. ROM is permanent, it's non-volatile, and it is strictly read-only, so that vital BIOS startup data can never be accidentally altered or deleted. But this leaves us with a pretty big question, right? If RAM is wiped clean every time we turn the computer off, and ROM only holds startup instructions, where in the world do we keep our massive files permanently?
Section 4. The Backing Storage Vault. Permanent Data Storage.
Well, that brings us to our next stop, the backing storage. Look, RAM and ROM are absolutely vital, but they have strictly limited capacity. To permanently store the huge amounts of data we generate every day, our photos, our music libraries, those giant software applications, we rely on backing storage. This is your vault, usually taking the form of an internal hard disk drive, an HDD, or a solid-state drive, an SSD. They offer permanent retention, massive capacity, and frankly, they're considerably cheaper per byte than those fast internal memory chips.
So the crucial point is understanding the system's primary bottleneck, known as the addressability rule. Despite how massive and important your storage vault is, backing storage is not directly addressable by the CPU. Let that sink in for a second. That brilliant CPU brain we talked about, it cannot talk directly to your massive storage vault. It's kind of like having a world-class master chef who isn't actually allowed to go into the pantry.
To resolve this strict bottleneck tension, the system relies on a very specific workaround. Before the brain of the computer can process any saved file or application, that data must first be moved out of the massive storage vault and loaded into the active workspace. It has to migrate into the RAM waiting room, if you will. Only once the data is sitting safely in RAM can the CPU actually reach in, fetch it, and process it.
Section 5. Input and Output Bridges. Human-Machine Boundaries.
So we cross the boundary between human and machine using interaction bridges. On one side, we have input devices. This is human-to-machine communication. It's exactly how we enter direct data or instructions through our keyboards, mice, or microphones. On the flip side, we have output devices. This is machine-to-human communication, where the computer takes that raw processed data and translates it back into a human-readable format, like text on your monitor or sound pumping through your speakers.
And this brilliantly illustrates a fascinating engineering reality known as complexity asymmetry. You see, translating our messy, unpredictable human actions, like typing, clicking, or speaking, into precise digital commands requires incredibly complicated engineering. Input devices are highly complex. Output devices, on the other hand, are generally much simpler. They basically just receive perfectly structured digital signals from the CPU and turn them directly into physical outputs like light, sound, or printer ink.
Section 6. The System in Motion. A Synchronized Loop.
All right, we've got all the puzzle pieces on the table now. We understand the ecosystem, the CPU, the memory, the storage, and the bridges. Let's bring the whole shebang together and watch the kinetic flow of this machine in action. Step 1. An input device triggers an action from the user. Steps 2 and 3. The requested data is forcefully migrated from the backing storage drive into the active workspace of RAM. Step 4. The CPU fetches that data from RAM, performs its complex calculations, and fires the result right back to RAM. Step 5. Finally, RAM pushes that final processed result to an output device, like your monitor, or it commits the changes permanently back to the storage vault. It's a continuous, beautifully synchronized, lightning-fast cycle of input, memory, processing, and output.
And there you have it, the foundations of computer hardware and architecture laid completely bare. You now possess a clear, concrete map of how invisible software instructions guide the internal brain, those temporary workspaces, and the massive vaults to turn raw human input into extraordinary digital reality. So my final question for you is this. Now that you actually know how the machine's anatomy synergizes to give you this much power, what reality will you build with it? Thanks so much for learning with me today. Keep exploring, keep questioning, and I'll catch you on the next explainer.